Welcome to the course on error control coding and introduction to linear block codes. Today in this lecture, we are going to describe what we mean by generator matrix and parity check matrix. So, we will continue our discussion with introduction to linear block codes. We will first describe what is a generator matrix and what is a parity check matrix and how are they related. So, as we described in the last class, an encoder for a linear block codes, what it does, it takes a block of k bits and maps it to n bit. Now, the matrix, we can use a k cross n matrix to define this mapping from k information bits to n coded bits, and this matrix is basically our generator matrix. For an nk linear block code, the mapping of k information bits to n coded bits is defined by this generator matrix G, which is of rank k. So, if we denote the information bits by u and we denote our coded bits by v, then we can write v as u times g, where our u is 1 cross k vector and this is generator matrix is k cross n matrix and our output coded bit is 1 cross n vector. So, as the name suggests, basically generator matrix is used to generate our code word. So, we generate our code words using this generator matrix, and this generator matrix gives a mapping between the information bits u to the coded bits v. So, how do we find code words? We find code words by taking linear combinations of rows of these generator matrix. In case of binary codes, so then these entries in the generator matrix are either 0 or 1, depending upon which bits are used to generate a particular coded sequence. So, we form a set of 2k code words by taking linear combinations of rows of these generator matrix. So, we can, as I said, we can write our coded sequence as u times g, which is basically linear combination of rows of the generator matrix. So, these are basically linearly independent k rows and the rank of this generator matrix is k. Since we are without loss of generality, since we are talking about binary linear block code, so we will be doing this addition modulus 2. So, what are the properties of a linear block code? Sum of any two code words in a linear code is also a valid code word. So, if v1 and v2 are valid code words, then v1 plus v2 will also be a valid code word. Also, an all 0 code word is a valid code word in any linear block codes. So, we can define a linear block code, nk linear block code, as a k dimensional subspace of vector space Vn of all binary n tuples. So, we can define a linear binary block codes as a k dimensional subspace of vector space Vn of all binary n tuples. Now, let us take an example to illustrate what is a generator matrix. So, in this example, we have considered 3 information bits and 6 coded bits, and in this table I have given you the set of 8 information sequences and their corresponding code words. So, how do we find the generator matrix in this case? So, we will have to look at each of these code bits and see how are we generating these code bits in terms of message bits U0, U1 and U2. So, first thing we are going to do is look at each of these code bits V0, V1, V2, V3, V4, V5 and write them in terms of U0, U1, U2. Okay. So, let us look at each of these. So, V0 is U1 plus U2, we can see easily V0 is this column and we can see this is same as U1 plus U2. So, U1 plus U2 in this case is 0, U1 plus U2 is 0, 1 plus 0 is 1, 1 plus 0 plus 1 is 1, 1 plus 1 is 0 modulo 2 and 1 plus 1 is 0 modulo 2. So, this V0 is basically given by U1 plus U2. Similarly, we can see V1 is given by U0 plus U2 and V2 is given by U0 plus U1. So, let us just check again, let us say V2. V2 you can see is given by U0 plus U1. We can check V2 is given by, so U0 plus U1, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1 and 1 plus 1 is 0. Similarly, we notice that V3, V4, V5 are nothing but information bits U0, U1 and U2 respectively. So, let us go back. V3 is this column and we can see this is same as U0, 0, 1, 0, 1, 0, 1, 0, 1. Similarly, V4 is equal to U1 and V5 is same as U2. So, now we have written our coded bits in terms of our information bits. This set of 6 equations, I can write it in a matrix form. So, I can write my coded bits in terms of information bits and this matrix G, which is our generator matrix, will tell us how are we generating each of these coded bits as a linear combination of these information bits. So, if we compare each equation, let us look at V0. So, what is V0? V0 is U0 G00 plus U1 G10 plus U2 G20. And what do we see here? V0 is U1 plus U2. So, that means G00 is 0 because there is no U0 term here, G10 is 1 because there is a U1 term here and G20 is 1 because there is a U2 term here. So, this will be 0, 1, 1. Similarly, look at V1. V1 is U0 G01 plus U1 G11 plus U2 G21. And if we compare it with V1 here, we see V1 is U0 plus U2. That means this G01 should be 1, G11 should be 0 and this should be 1. Likewise, we build up the other columns of this matrix. So, if we do that, what we get is something like this. We can verify basically, let us take second last column. So, what is V4? V4 is U0 times G04 plus U1 times G14 plus U2 times G24. And what is V4? V4 is U1. So, then this should be 1 and this should be 0 and this should be 0, and this is what we have 0 1 0. So, now we can basically find out the generator matrix. So, a linear block code is completely described by its generator matrix, and as we said, we can use the generator matrix to generate our code words. For example, if my information sequence is 101, what should be my corresponding coded bits for the information sequence 101? How do I find that? So, as I know, my output code word is basically u times g. So, I will take linear combinations of rows of my generator matrix. What are the rows of my generator matrix? These are the 3 rows of my generator matrix. So, my coded bit corresponding to this information sequence would be 1 times G0 plus 0 times G1 plus 1 times G2. So, that is what I have written here. This is 1 times G0, 0 times G1 plus 1 time G2. So, this is basically 0. So, what I have is then this plus this, right. So, let us look at 0 plus 1 would be 1, 1 plus 1 would be 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0 and 0 plus 1 is 1. So, my code word corresponding to this information message bits, information bit is given by 101 101. Okay. Now, what do we mean by a linear code in systematic form? Now, if we are able to among the coded bits, if we are able to separate them out into, if the message bits appear directly in the coded bit sequence, then we can separate out the message bits from the parity bits. For example, go back to this example. What do we have here? We have 3 of these coded bits exactly same as information bits, and the other 3 bits, parity bits, are linear combination of these message bits. So, from the output code word we can clearly separate out the information sequence, which is in this case V given by V3, V4 and V5. So, in this case V1, V2, V3 are these n minus k parity bits, and V3, V4, V5 are my information bit. So, in this particular example, we can see that we are able to separate out information bits directly from the coded bits. So, in a systematic, a block code in a systematic form, we are able to separate out the information bit part from the coded bits. So, a generator matrix for a linear block code in systematic form will be of the form like this, or it would be basically I times Ik times some either of this form. Now, why do we say that? So, only when we have a part of a generator matrix of the form of identity, then what is going to happen? When we multiply our information sequence with this sort of generator matrix, you will see part of my coded bits will just depend on one particular information bit sequence. So, if I write down the corresponding equations for coded sequence, what you will see that some coded bits directly depend on the message bits, and then rest are, which are parity bits, are linear combination of these message bits. So, in a systematic form, basically we can separate out the message part from the parity bit part. So, as I said, for a systematic linear block codes, the message part will consist of the k information bits, and the remaining n minus k bits, which are the parity bits, basically they will be linear combination of these message bits. So, we can write down the encoding equations for these matrices, for the systematic code. So, if you look at what is our encoding equation, our V is U times G, where G is of form like this. Okay. So, if we write U, which is basically U0, U1 to Uk minus 1 times this G matrix, what we will get is a form like this. So, you will have n minus k parity equations, parity check equations, which are given by this expression, and then you will have remaining k unaltered message bit. So, for a linear block code in a systematic form, the encoding equations will be of this form. And as I said, since we are restricting ourselves without any loss of generality to binary code words, this addition is basically done modulo 2. So, what we have seen so far is we can describe a linear block code by its generator matrix, which is a k cross n matrix, and we can use this generator matrix to generate our set of code words. Now, there is another matrix which we call parity check matrix, which is related to our generator matrix, we will show, which can also be used to completely describe a linear block code. So, for a nk linear block code can be specified by a n minus k cross n parity check matrix, which we denote by H. The generator matrix we denote by G, and the parity check matrix we denote by H. Now, this parity check matrix has this property that if V is your valid code word, if and only if V H transpose is going to be 0. So, if V is a valid code word, V H transpose will be 0. So, let us see how we can derive our parity check matrix from a generator matrix, and what is the relation of the generator matrix to the parity check matrix. So, we will take an example of a 7-4 systematic linear block code whose generator matrix is given by this. So, since this is a systematic code, we can write it of the form P times this I k, this generator matrix can be written of this form. Okay. Now, from this generator equation, we can write our coded bits in terms of our message bits. So, let us do that. So, the encoding equation, since this was our generator matrix G, this is our information bits, message bits U, and this is our coded bits V. So, we can write V as U times G. So, it is a 7-4 code. So, there are 4 information bits, I denote them by U0, U1, U2, U3, and there are 7 coded bits, I denote them by V0, V1, V2 to V6, and this generator matrix I have already given you this. So, I can write down the encoding equations. We do that, you can see from this what is V0, it is U0 plus U2 plus U3. There is a typing mistake here, this should have been U2. So, V0 is U0 times 1 plus 0 times U1 plus 1 times U2 plus 1 times U3. So, this V0 is given by U0 plus U2 plus U3. Similarly, what is V1? V1 is given by U0 plus U1 plus U2. V2 is given by U1, U0 into 0, U1 into 1, U2 plus U2 into 1 plus U3 into 1. So, V2 is given by U1 plus U2 plus U3. So, that is what I have here. What is V3? V3 is given by U0 into 1 and rest are all 0. So, V3 is nothing but U0. Similarly, V4 is U1, V5 is U2 and V6 is U3. So, I now have set of 7 coded bits, and this shows the relation between the coded bits and information bits. Now, since we are restricting ourselves to binary codes, we can even write this equation like this: V0 is plus U0 plus U2 plus U3 is equal to 0, correct? Because this V0 V1 is nothing but parity bit, which is basically like 1 or 0. So, if we add this to this, modulo 2 sum will be 0. So, this similarly we can write as V1 plus U0 plus U1 plus U2 equal to 0, and this can be written as V2 plus U1 plus U2 plus U3 is equal to 0. The next what we would try to do is, we would try to write these parity check equations in terms of other coded bits. So, we can see here U0 is nothing but V3. So, wherever U0 appears, we can replace it by V3. Similarly, U1 is equal to V4. So, wherever U1 appears, we can replace it by V4. U2 is equal to V5. So, we can replace U2 by V5, and U3 is equal to V6. We can replace U3 in terms of V6. By doing this, what we will get is set of equations which basically are dependent on these coded bits. So, if we do that, what we get is something like this. The first expression basically, which was V0 plus U0 plus U2 plus U3. Now, this can be rewritten as V0 plus what is U0? U0 is V3, V3 plus what is U2? U2 is V5, V5 plus what is U3? It is V6. So, V0 plus V3 plus V5 plus V6 is 0, and that is what we have here. V0 plus V3 plus V5 plus V6 is equal to 0. Similarly, we can write the other equations as well. Here also we will replace U0, U1, U2 by V3, V4, V5, and what we will get is V1 plus V3 plus V4 plus V5 is equal to 0, and similarly the last parity check equation can be written as V2 plus U1 is V4 plus U2 is V5 plus U3 is V6. So, that is what we have here. V2 plus V4 plus V5 plus V6 is equal to 0. So, now we have set of encoding equations in terms of coded bits. Next, the same thing we can write it in a matrix form. So, I have my coded bits V0 to V6. I have 3 sets of parity check equations, this and this, and the same thing I can write it in a matrix form like this. Now, you can see these are equivalent. So, let us look at first equation. This is V0 plus V3 plus V5 plus V6 is 0. So, you can see which are the elements which are. So, V0 times 1, this is V3 times 1 plus V5 times 1 plus V 6 times 1. So, that is what is why this equation. Similarly, you can see this equation, this V 1 plus V 3 plus V 4 plus V 5 is equal to 0, and this last equation, this is V 2 plus V 4 plus V 5 plus V 6 is 0. And what did we say about parity check matrix? We said that if H is a parity check matrix, it is an n minus k cross n matrix, and it has this property that V H transpose is 0. So, we have, can write this as, this is my V, this is my H transpose, V H transpose is 0. So, then what is my H matrix? H matrix is a transpose of this matrix. So, this will be 1 0 0 0 1 0 0 0 1 1 1 0 0 1 1 1 1 1 and 1 0 1. And this is my, so for the 7 4 code, this is basically 3 cross 7. As I said, n minus k cross n matrix. This is my parity check matrix corresponding to this same code which is generated by this. Another interesting property that you can basically see is, so V H transpose is 0, I can write this as U times G H transpose is equal to 0. In other words, G H transpose is 0. So, what does that mean? The rows of G matrix and rows of H matrix are orthogonal to each other. So, the H lies in the null space of G. So, as we can see from this, that generator matrix and parity check matrix are related to each other, and they have this property that rows of G matrix and H matrix are basically orthogonal to each other. So, if you have a systematic code whose generator matrix can be written in this form, because H lies in the null space of G, we can write down its corresponding H matrix very easily, and this is basically given by, so if a generator matrix can be written of the form P and identity matrix, we can write its parity check matrix as identity matrix and P transpose. So, let us take an example of a generator matrix of a systematic code. This is a systematic code. We can see, we can separate out this generator matrix as some matrix P and some identity matrix. So, this we can write as the H matrix, we can write as identity matrix and P transpose. So, then this can be written as 1 1 0 is 1 1 0, 0 1 1, 0 1 1, 1 1 1, 1 1 1, 0 1 0. So, this is my H matrix corresponding to this. So, whether you are given a generator matrix or a parity check matrix, your linear block code is completely specified by either of them. And as I said, we use the generator matrix to generate our code, set of code words, whereas parity check matrix, as the name suggests, is used to check whether the parity check constraints are satisfied. As we said, basically parity check matrix has this property that if V is a valid code word, if and only if V H transpose is 0, and we use this property in decoding, and that is why you see the name parity check matrix, because this matrix H is essentially used to, in some sense, check whether the parity check constraints of the code are satisfied or not. Thank you.